Welcome back to the deep dive. Today, we're jumping into the Online Encyclopedia of Integer Sequences, the OEIS.
A fantastic resource.
Absolutely. And if you're into number theory, maybe a student, or just fascinated by patterns, this is for you. We're tackling sequence A000253 today.
Right.
It's about binary strings, specifically those with a certain pattern. So our mission really is to figure out what the sequence is, how it works, and, why it's interesting in combinatorics. Let's unpack it.
And what's really exciting, I think, is how the OEIS connects these abstract number sequences to very concrete counting problems.
Moments, you mean?
Exactly.
Yeah.
A00253 is a perfect example. We'll see how a formula translates directly into counting things you can almost picture.
Okay, I'm ready for that. Let's start with the basics. The definition. It's given by a recurrence relation.
That's the primary way it's defined, yes.
Which means each number depends on the ones before it.
Precisely. A recurrence gives you the rule to get the next term from previous ones.
Yeah. And for A000253, the formula involves the three previous terms, AN1, AN2, AN3, plus this extra bit, 2 and 1.
Correct. That 2 and 1 term is what makes it a non-homogeneous linear recurrence. It's an input that depends on the position n, not just the previous sequence values.
And that affects the growth.
It adds a distinct layer to how the sequence behaves, yes. And crucially, the OEIS entry mentions offset 0,3.
Ah, right. That tells us where to start, like the initial values.
Exactly. It tells us the first term corresponds to n0, and the recurrence formula itself really kicks in from n3 onwards. Those starting values 0, 1, 4 are essential. Without them, the recurrence alone isn't enough to pin down this specific sequence.
Okay, so speaking of the values, let's get a feel for them. It starts 0, 1, 4, 11, 27, 63, 0.142, 3, 12, 6, 7, 3. I mean, they grow really quickly. Doubling, more than doubling sometimes.
They accelerate quite dramatically.
You can almost, feel the complexity just hearing the numbers jump like that. So what are these rapidly growing numbers actually counting? That seems to be the core question.
It is. The numbers are interesting on their own, but the meaning is where the real insight lies.
And this is where Holger Petersen comes in. According to the entry, he figured out the combinatorial meaning.
Yes, and here's where it gets really interesting.
Okay.
Petersen showed that ANN is the number of binary strings of zeros and ones of length n plus 2.
N plus 2, okay.
That contain the specific pattern 0, 10.
Wow. Okay, wait. So these numbers, 0, 1, 4, 11, 27, they're literally counting how many ways you can arrange zeros and ones in a string of a certain length so that 0, 10 appears somewhere inside.
Precisely that. The abstract numbers map directly to counting these specific arrangements.
That's a fantastic connection, finding that pattern hidden in the numbers. But how does counting strings lead back to that specific recurrence relation we started with, one with AN1, AN2, AN3, and the 2 and 1? It seems like a leap.
It does seem like a leap initially, but Petersen's proof builds it step by step. It's quite elegant, actually. It's all about how you construct longer strings from shorter ones. Think about a string of length, say k. If it already has the 0, 10 pattern inside it,
right,
then if you add a 0 or a 1 to the end to make it length k plus 1, it will still contain 0, 10.
Makes sense. Once it's there, it stays there when you extend it.
Exactly. So for all the strings of length n plus 1 that already had the pattern, you can append either a 0 or a 1. This accounts for roughly doubling the count, which relates to the 2an1 part of the recurrence.
Okay, that explains the doubling part, the 2an1. But the recurrence also has subtractions, an2 and plus an3, and that plus 2n1. Where do those come from in the counting?
That's the clever part. We've only considered strings that already had the pattern. We also need to count the strings that gain the 0, 10 pattern for the very first time when we extend them.
Ah, the new ones.
Yes. Petersen carefully analyzes the strings that don't have 0, 10 yet. For example, consider strings of length n plus 1 that don't contain 0, 10 but happen to end in 0. If you append 10 to such a string, you might create the 0, 10 pattern right at the end. But you have to be careful not to double count or miss cases. The proof involves tracking strings without 0, 10 based on how they end, like ending in 0 or 0, 1 and so on.
So it's keeping track of strings that almost have the pattern.
In a way, yes. By meticulously adding the counts from strings that already had the pattern and carefully adding the counts of strings that just formed the pattern and subtracting overlaps or cases handled by previous terms, Petersen's argument reconstructs the entire recurrence relation. AN exceeds 2A and Nash 1. AN2 plus AN3 plus 2 and NAS1.
Wow.
It's a beautiful piece of combinatorial reasoning. It shows exactly why the sequence behaves like this. connecting the abstract formula directly to the process of building and counting these binary strings.
That really clarifies the connection. It's not just a formula, it's derived from the counting process itself. Now, another thing I find fascinating in the OEIS is that you often see multiple ways to define the same sequence.
Very common, yes.
Like, Ralph Steffen gives a formula linking A0000000253 to A00000079 and A00007251. Why have all these different formulas? Isn't one enough?
That's a great question. Think of it like looking at a sculpture from different angles. Each formula, each perspective can reveal something different about the sequence's nature or its relationship to other mathematical objects.
So different formulas highlight different connections.
Exactly. One might make its connection to generating functions obvious. Another might reveal a link to matrix representations. And sometimes, like we see mentioned with the signature 453-2.
Right, what's that about? It looks different from the first recurrence.
It implies that A000253 can also be described by a homogeneous linear recurrence, but one of a higher order 4 in this case. So the same sequence can satisfy both a non-homogeneous recurrence of order 3 and a homogeneous one, order 4. It shows the sequence has multiple layers of structure.
Interesting. So these different descriptions aren't contradictory, they just offer different insights.
Precisely. And this richness leads us to how mathematicians actually work with these sequences. You can't just rely on pen and paper for long.
But the numbers get huge. This is where computers come in.
Absolutely.
Yeah.
The OEIS entry itself often gives code examples. You see maple code using recursion with memoization.
Memoization, is that like caching?
Essentially, yes. It tells the program to remember results it's already computed so it doesn't waste time recalculating. Hugely speeds things up for recursive definitions.
All right.
Then there's often a matrix method mentioned. Using matrix exponentiation from linear algebra can be incredibly fast for calculating terms of linear recurrences.
Wow. Linear algebra to crunch sequence terms. What about other tools like Mathematica?
Similar options there. You might see code using generating functions expressing the sequence as a power series and extracting coefficients, or using built-in functions like linear recurrence, perhaps using that 4532 signature we mentioned.
So these aren't just theoretical definitions, they translate directly into practical ways to compute and explore the sequence.
Exactly. These tools are vital. They let researchers verify conjectures, explore patterns, and generate terms far, far beyond what you could do by hand. The fact that someone like Eloise Hines provides a table of the first 1,000 terms, well, that's only possible because of these computational approaches.
It really shows how computation is woven into modern mathematical exploration. And you mentioned earlier, sequences in the OEIS aren't isolated islands, they're connected.
Deeply interconnected.
The entry lists cross-reference to other sequences like A119706, A0344345, and so on, and adjacent sequences too. Why are these connections so important?
Why care about the connections? Well, finding a link between your sequence and another might mean a problem you're working on is related to a problem someone else has already studied, maybe even solved.
So it's about leveraging existing knowledge.
Precisely. It helps you understand the underlying structures. If sequence X relates to sequence Y, maybe techniques used to analyze Y can be applied to X. It avoids reinventing the wheel and reveals deeper mathematical themes.
And the entry also has keywords like for non-negative.
Little labels that help categorize.
And names the author, Jason Howald, and notes it's approved. It feels very curated.
It is. There's a whole editorial process.
Yeah.
And notice the modification date, June 18th, 2025. Today.
Whoa, it was updated today.
It shows how dynamic it is. People are constantly refining entries, adding references, correcting details. It's a living encyclopedia, a global collaboration.
That's incredible. A real-time mathematical project. So we've gone from this recurrence relation.
AN to AN-1, AN2 plus AN3 plus 2N1.
To understanding it counts binary strings of length n plus 2 with 0, 10 inside. We've seen it has multiple definitions, connections to other sequences, and powerful computational tools behind it, all wrapped up in this amazing resource, the OEIS.
It really is an invaluable tool for anyone exploring numbers and patterns.
What a fascinating dive. It makes you realize the depth behind seemingly simple sequences.
It does. And here's a thought to leave you with. We looked at the pattern 010. What happens if you change the pattern? Maybe to 1000 or 1010.
Yeah.
Or what if you weren't using binary strings, but maybe strings with 3 symbols, 0, 1, and 2? How would the counting change? How would the recurrence relation change?
Would it even have a nice recurrence?
Maybe, maybe not.
Hmm.
Slight changes to the problem can lead to completely different sequences, sometimes related, sometimes wildly different. The OEIS is packed with these variations. So maybe look around you, find a pattern in data, in nature, anywhere, and see if you can find its sequence in the OEIS. You might uncover some surprising mathematical connections.